And we're going to see how we can use what we already know about graphing and about polynomial functions and use some technology to solve these problems. What page? This is on page 57 at the bottom. So if you drew a suitcase, and we're going to make an assumption here, what assumptions did you make? That your suitcase is basically a rectangular prism. And they say that you can't have the width, the depth, and the length altogether can't be more than 100. And they say several models have a length 10 centimeters greater than the depth. So if I call my depth x, they say several models have a length here that's x plus 10, and then they would have some sort of width. I'm going to start with a W there for width.
Yeah, if you agree to that, would be nice. Sometimes happens.
You can go to the washroom if you need to.
No, it's gonna be over in like 5-8 minutes. This happens every 2 weeks or something.
I thought you were going to say every 2 minutes.
So.
It'll stop in 5 minutes every 2 minutes.
It'll stop in 2 minutes, but just in this case.
Now, this W is dependent on the other ones. For example, if x is 20, does it make sense the other side here would be 30? And then what would be left for the W? 50. You can do that mental math pretty quickly, right? And if I said, oh, but if x was 10, this would be 20. What's left over here? 7. Because they have to, if you want to make it a maximum, it has to add up to 100. So now, if you can do that with numbers, we want to use the same variable all the way through. If this is x, and this is x plus 10, how much is left over there?
You write it as 2x minus 9, or 90 minus 2x.
90 minus 2x. Because you would take your 100 that you started with, right? You would subtract this x, and then you would subtract this x plus 10. We'd have to put that in brackets, because you're subtracting all of it. And that would give you 90 minus 2x. And if we can get everything in terms of x, we can write out the volume. Length times width times height in no particular order. And this volume is a polynomial already in factored form. And because it's already factored, you could find the x-intercepts easily. We could think about its end behavior, and we could draw a sketch of this graph. In fact, that's what we're going to do. Okay? First of all, can you see that the x-intercepts are x equals 0, x equals negative 10, and x equals 45. If you were asked to find the y-intercept, that'd be plugging in 0 for x. Well, because the x-intercept's at 0, your y-intercept is also at 0. So we have 0, 0 for our y-intercept. If I were to rewrite this equation, starting with the highest degree, check out your x's. Do you see if you multiplied those together, you would get a negative 2x cubed dot, dot, dot. And because of that leading coefficient being negative and the fact that it's an odd degree, you know your end behavior will act like a line with a negative slope. So we know that that's our end behavior. We've got all of our x-intercepts, we've got our y-intercepts, which means we have enough information to draw this graph. Now when I'm going to go draw this graph, because one of my x-intercepts is 45, I'm not going to do little ticky marks until I get to 45, because that would take a long time. I'm just going to go, I like this to be 45. Would you agree that based on that, maybe here would be negative 10? Does that look approximately to scale? And we have x-intercepts at 45, at 0, and at minus 10. And because the end behavior looks like this, And because the multiplicity of each x-intercept is 1, you know your graph has to go straight through each of those x-intercepts. So now when I'm drawing my graph, nice smooth curve, straight through, straight through, straight through, ends down there. Here is the graph that we're working with. Now sometimes in these questions, they're going to ask you about domain. And normally if we had an x cubed graph, we would say the domain is everything. But when you're dealing with a real life situation, now some things don't make sense. Like for example, what did we graph? We graphed volume equals x. So this is x, which happens to be my depth, and this is volume, the volume of that suitcase. Question.
Yeah, my question was, how do you know that like the thing has a giant one, not like
You don't. I don't know how high this goes, but we are going to try to figure out this value today.
Okay.
But as far as the domain goes, it's like, wait a second, does a negative volume actually make sense? This would be like the suitcase where you throw your socks in and they just disappear. No, we can't have a negative volume for our function. So that doesn't make sense. Can you have the height be negative? No. Only thing that really makes sense in this situation is this part here. From 0 to 45. And I don't mind if you use round brackets or square brackets here. Technically, a square bracket would mean you have a height of 0, which you have a suitcase that just looks like a thin piece of paper. Be kind of useless, really useless, but I guess possible. So you'll see sometimes maybe the textbook includes 0 and 45. I would accept either, including 0 and 45 or not, because it's really kind of like based on the real situation. Can you really have a height of 0? But then someone might argue, could you really make a suitcase with a height of 0.1 centimeters? I guess you could, but again, why would you? So if this is the only part that makes sense, we want to find this highest point, that maximum. And we're going to do that today using technology. So the first thing we're going to do is we're going to take out our graphing calculators, or at home you can use Desmos. But not your phone, unfortunately. And we're going to type in x times by x plus 10 times 90 minus 2x. And chances are you've probably got your window on its standard setting, so when you hit graph, it looks like this, which is really useless. So it's important when you're using technology that you have already graphed it by hand and get an idea. What do I want to see? I want to see this. That would be a nice window. If I do that, can you see that I want to go past 45? And I want to go probably higher than I have. So going past 45, so if I hit my window button, I've got an X-min. I like to keep a little bit negative just so I can see my y-axis. And my maximum, if I want to see 45, maybe I go up to 50. Now if I hit graph right now, I don't see the maximum point. I need to see higher. So a couple of things that can help you with this. Okay? First, to get an idea of what kind of numbers I'm looking at, you can try something. Like, remember when you said 20, 30, and 50 was a possibility? Let's figure out that volume. If I used 20 times 30 times 50, that's already at 30,000. Okay? Because typically, what do I see students do? Oh, 10 wasn't enough. I'll try 20. And then be like, oh, 20 wasn't, maybe I'll jump to 50. We already know that it's at least 30,000. So, 30,000. I know it's at least that, so this is not a good choice, but I'll go a little bit bigger. Will I see the maximum? Probably not, no. But at least it's closer.
Another good spot to start off with finding the height is just zoom in.
Right, there's also under the zoom fit. There's also above graph, this table, really helpful. It makes a table of values for you, and you can scroll through from 0 to 45 and see what's happening. Oh, it's getting bigger. There's my 30,000.
There we go.
Oh, it looks like it's maxing out at 36,000. So I might go to my window and go 40,000. The zoom fit sometimes really works nice and sometimes really disappoints you. So once I got 40,000, now I've got my graph and I have that maximum showing up. Everything you want to calculate on your graphing calculator about graphs is above the trace button in Calculate. So if you go second, trace, to that calculate menu, you could go to number 4, which is a maximum. It asks you to start on the left. My cursor is to the left of the maximum. I push enter. It draws a line. Then it asks you to go to the right, so we can move our cursors over until we're past that maximum. Now my cursor's on the right. I push enter again. As long as the maximum is in between those two lines, push enter, and it finds it to be 36,209 and 28.581. I'm going to cheat and just drag this here so I don't have to flip back and forth. Nice. Don't you wish you could do that? Just drag your calculator's screen to your notes. So let's read the question. What did they all want us to find? Okay, write a polynomial function. We did that. Graph the function. We did that. To the nearest cubic centimeter, maximum volume. Max volume is, to the nearest cubic centimeter, oh my goodness, 362, oh, fancy. Fancy rounding. 36,210 centimeters cubed. Next question. What are the dimensions to the nearest 10? Oh, I'm going to show you something that's really cool. First of all, I'm going to show you that most of you would make an E6 error in the following. Okay? You see that the X is 28.5 or 28.6. Oh no, I don't think you make, maybe. But I want to show you something cool about this anyways. 28.6 centimeters by, and then the other one would be add 10, so that I don't think you'd make a mental math error in that. 38.6 centimeters by, and then you have to figure out what adds up to 100. So we're going to figure out that we need, I guess we could go to our calculator here. I'm going to just show you something cool on your calculator. After you've done some calculations on your graph, if you hit the store button, nothing happened. This could be a problem. I'm just going to see if it gives me an error. Yes. Okay. Let me go back to my graph. Let me go second, calculate my maximum again. Because I was hoping to show you something cool. That wasn't working. So after you've calculated, if you go out of here, oh my goodness, and hit store, it says, where would you like to store your answer? I'm going to just store it as X. And that answer is the last thing you solved on your graph, which is sometimes really helpful. So you can take stuff you've solved on your graph and not lose any decimal places. So if we do 100 minus X minus X plus 10, I guess I could have done 90 minus 2X. 32.8 centimeters is our last value. Did the question ask us to solve anything else?
That's what assumptions we made.
Right, we talked about already that we assumed that this was a rectangular and not a suitcase that was another weird shape. Also, when you get an answer, it's not bad to like think about it and visualize it. So first of all, 28.6 centimeters, that's just a little bit longer than a ruler. That's a pretty deep suitcase. This one is pretty boxy. Almost seems unrealistic when I think about its shape. The volume, though, I want you to imagine that volume. Can you picture that as a volume? Probably not. We're probably not too good at thinking in cubic centimeters. Do you know how big a cubic centimeter is? Like 1 centimeter by 1 centimeter by 1 centimeter? A little tiny square like that? We have 36,000 of those. It's really hard to visualize a lot of little things. Now, volume, cubic centimeters. Have you seen cubic centimeters ever, like when you got a vaccine? Sometimes they say you'll need 10 cc's of something. Have you ever heard that language in talking about medicine? The cc stands for cubic centimeters. And did you know that 1 cubic centimeter is exactly 1 milliliter? So if you have that little tiny cup, you could drink a milliliter in a 1 cubic centimeter.
Why don't they just say milliliters?
I don't know. CC sounds fancy. Or it might be that, like, I think because when they pull it in a syringe, yeah, could be either one. I don't know, because it's filling up space. And the space is a measurement of volume, which is a measurement of centimeters.
So this is 1,000 cubic centimeters?
That is 1,000 cubic centimeters.
So there's 3 of these.
No,
There's 30 of them.
36 of those.
Which is a
Okay,
pretty
so
decent size for a
1,000 milliliters is a liter, and this is 36 liters. Second thing, have you ever seen luggage sold by liters? What did you see that was sold by, that had liters as its measurement?
I don't know, but I feel like I've seen something sold by that before.
Because often backpacks, especially for traveling, are sold by liters. If you go to Mountain Equipment Co-op and look at their backpack, they'll be like, this is an 85-liter backpack. It's like, great, I would like to fill it full of water. That's what I was hoping to do. But they measure it in liters because a backpack isn't square, it can expand. So they're like, if we filled it full of water, this is how many liters it could hold. I like to think of, if I was traveling here, 36 liters, this would be. A thing that I like to visualize is a pail of ice cream, the big ones, the 4-liter pails of ice cream. You could fit 9 of them on your carry-on. I would like the security to see that as it's going through. You have 9 pails of ice cream in your carry-on. I think that could end up being quite disastrous. All right, so let's go to example 1. Example 1 is going to be very similar to your jewelry box question. And I think it's a really neat question because getting the maximum volume out of a concept like this could be really useful for manufacturing and for saving companies money. They want to pack as much things into something as possible while minimizing how much materials they use. So this is a very, I think, neat and useful problem. So in this question, they started off with a rectangular piece that was 25 centimeters by 30 centimeters. And they cut squares out of the corners, just like we did. And if you fold it up, it would make an open box just like that. So it makes sense that if we call the side of the square that we cut out as X, that the height of our open box is going to be x. Then there is a short side and a long side now to this open box. Does it make sense? The short side started at 25, but then you cut off x and cut off x,
So -2.
minus 2x. And the long side similarly started off as 30, and you took off 2 x's, so we get 30 minus 2x. This is the visual of what's happening. Now they ask us to do a bunch of things. Write a polynomial function to represent the volume. Well, volume is length times width times height in no particular order. And it's super nice because it's already in factored form, each with a multiplicity of 1. In fact, you could find your x-intercepts really quickly and easily. X equals 0, x equals 12.5, and x equals 15. Your y-intercept, if you plugged in 0 for x, obviously you would get 0 for y as well. We're going to need our x-intercepts, y-intercepts, and our end behavior to graph this. So if I want to figure out my end behavior, I'm going to have to look at all my x's. And if these were all multiplied together, can you see that you would get volume equals a positive 4x cubed plus ... So this is an odd function with a positive leading coefficient. There's our end behavior. Now we can do the rough sketch of our graph. 15 is the biggest number, so I'm going to pick 15 here. 12.5 then would be about maybe here. So 0, 12.5, and 15. Based on my end behavior and the multiplicity of each of those being 1, I'm going to start down here, straight through, straight through, straight through. What is its domain? Okay, again, what do these things stand for? This is volume, this is x. We can't have a negative volume, right? Okay, so volume is positive in this section and also in this section. My question is, why is the domain only going to be this part, but not that part? Like, why can't we have that red part where the volume is positive? Yes.
That is because that is after the volume has already reached below the possible, below what is possible.
I'm saying, okay, but why don't we just ignore that part and start on the other side then? What's wrong with those numbers farther to the right? And usually to figure out what's wrong, you have to think about the context of the question.
Because that's bigger than the actual side of the box.
Like, if we look back at our picture, do you see the x is the little square that you're cutting out? If you cut out something bigger than 15, what's going to happen to your 25 side? It's going to be non-existent. You have no paper left, and somehow you're like, this has a huge volume. Even though there's no paper left, it doesn't make sense. Right? So sometimes, even though the function looks like it makes sense, we have to consider the context. And so in this context, the domain only makes sense from 0 to 12.5. And we want to find this max. So again, we're going to type this into our calculator. X, and then we had 25 minus 2x and 30 minus 2x. And if I hit graph from my old window, it's not the greatest graph, but it would be enough. You could find the maximum. This is the part that made sense, right? But we might go back to our window and say, well, if I'm only considering up to 12.5, maybe I change my x max to 50. And now when I hit graph, I'm like, that's still, I'm going way too high. So maybe I go to my table of values and check between 0 and 15. How high does it get? Looks like 1,500. So maybe I'll change this down to 2,000. That looks better. And now we can find our maximum. So go second, calculate the maximum. Now, there's two ways you can get to the left. One way is to act like a woodpecker and just keep hitting that arrow over and over and over again. Works fine on the graphing calculator. Sometimes if I do it fast enough on the computer, I cause the whole program to crash. Okay? The other option is you can just put a number in. I'm pretty sure 2 is to the left. So I just push 2 and enter, and sure enough, that's to the left. And it's a lot quicker. I'm going to say 8 looks to the right. Yes. Is my maximum between those two. Push enter again, and we find it to be right there. So I'm going to steal that graph off to the side and see what questions. They are notorious for asking tons of questions. Maximum volume to the nearest cubic centimeter. So max volume, 1512 centimeters cubed. Make sure you have your units, so you avoid E5. What is the size of the square? What length is it? And it didn't say what's around here, so I'm going to use 4.527, 3 decimal places. And then dimensions to the nearest 10.
Mr. Jerry, you're not getting 100%.
I would have caught it when I ran over my mark. 4.5 centimeters, because I was so excited about taking off an E6 air. If
What?
If you use 4.5 to find your other ones, you will get an E6 rounding error. So, and this is a good example of where should store this answer as x, because if I do 25 minus 2x, it comes to 15.9, not 16. And if I do 30 minus 2x, I get 20.9, not 21. Can you see yourself just doubling the 4.5 and getting 9? And doing 30 minus 9? This is easy mental math, and writing 21. So it's really easy to round early and get a mistake in this. Yes?
How can you have the size of a square not be square?
Okay, size, side, length, size of square. Good. Did they?
But it's asking me what size of square should be cut out, not what size length.
Oh yeah, then I have to do. Okay, you're right. You're right. I have to do area x squared. Or I could probably write it as what size of square? We could probably.
Couldn't you just write it as that square?
Or I could just write the dimensions. The dimensions of the square, 4.527 by 4.527. All right, questions for practice on this one are 3, 4, 5, 6, 9, and 10. Now, some of you might be thinking, or you're going to think this right after I tell you, is If we don't get a graphing calculator on our exam, then they can't ask us this question. You're right, not in this form. But I will show you what kind of question has been asked on an exam. Here it is. So turn to page 56. I'll give you some time to write this down. And this was, controversial. We'll talk about the controversy of this 5-mark exam question after you write it down. So it started off not too bad. Students actually did very well for the first mark of this question. That v of x is equal to x times x plus 2 times x plus 10. They might have even drawn x plus 2, and x plus 10. Nice. Then it says find all, and this is where the controversy came in, is what does that mean when it says find all the possible values of x, given that the volume was 96. So students plugged in 96, great, for the volume. And since this was a non-calculator question, most students were very astute in thinking it's probably not going to be 1.584 or something like that. It's probably going to be a nice number. So which number do you think they tried first? For x, 1. 11 times 3 times 1 is 33. Does that work? No. So what do you think students tried next? 2. 12 times 4 is 48 times 2 is 96. X equals 2. Then they wrote out the dimensions, 2 by 4 by 12, included their units and everything. And here's where the controversy started. Students who did that got 2 out of 5 and lost 3 marks, which people thought was overly harsh. Okay? When you guess and check, you don't know if you found them all. You have found one. In this case, it is the right answer and the only answer, but that's besides the point. You have found them all, because you wrote out the only answer. But you haven't shown that you knew that you found them all. You just show that you found one. So now, when questions like this come up, they often have new wording. Right? If the question says solve algebraically, that takes away your option of guessing and checking. Now you have to actually solve it. Well, this also poses a problem because many students look at this and go, how do I solve that algebraically? Well, the only way you could solve this being a cubic equation would be to factor it if the other side was equal to 0. So we actually have to multiply this out first. I'm going to choose to multiply these together and get x squared plus 12x plus 20. And then distribute your x and get 96 equals x cubed plus 12x squared plus 20x. And then we can move our 96 over to make one side equal to 0. And the controversy continues, because if this is non-calculator, and I'm going to let p of x equal all of this, now you would have to use your remainder theorem and synthetic division to factor this. But isn't the last number kind of big? Right? Like, whatever it works, the last number has to multiply to give us 96. So it could be 1 and 96, 2 and 48, 3 and, what would that be? Something big, 32, 4 and 24, 5 doesn't work, 6 and 6, like there's so many options. And mental math-wise, with the remainder theorem, I'm going to tell you, try 1 and -1, they don't work. Luckily, we already figured out the answer was 2. So if you tried p of 2, you would get 0, which means that x minus 2 is a factor, and you could go to synthetic division and put a 2 out in front. And 1, 12, 20, and negative 96. Bring down the 1. Multiply, add, multiply, add, multiply, and add. And yes, you get a remainder of 0.
Could you scroll a little bit up?
And we're not really going to write the division statement because we're trying to factor this. This other side is still equal to 0, so we would still write 0 equals, and now we have x minus 2, and we're left with x squared plus 14x plus 48. There's our division statement. And can we factor this even further? Yes, we can. So there are more answers. X plus 6 and x plus 8. So our answer of x equals 2 was not alone. X could also equal negative 6, and x could also equal negative 8. Wait a minute. What did x stand for? The x was the height of the box. So this answer and this answer actually make no sense in the real world. So the answer is only x equals 2. And your dimensions are 2 centimeters by 4 centimeters by 12 centimeters. And that would get you your full 5 out of 5. Because algebraically you've showed all the possibilities, canceled out the 2 that are not realistic. So I'm going to give you one like this on your test, and I will have the solve algebraically, where you have to multiply it out, move the 96 or whatever number over to the other side, and solve completely.
Did you put one of those on this?
No, I don't think I did.
So we'll just have to remember.
So you have to put a big star beside this one in your notes.
This is a question where, if you scroll down,
Yeah.
where did you get the 2 on the, like, the simplified, division thing there?
This 2
Yeah.
or this 2?
Yeah.
Because 2 in the remainder theorem gave me 0. Because I already cheated and figured that out with mental math.
Just like guessing?
Just I guessed it. Because I was like, it can't be that crazy of a number if it's going to be non-calculator.
So you had to guess to know that 2.
I know, it seems like a not fair question, right?
Yeah, I
But-
feel like because they didn't say algebraically, they shouldn't take the points.
That's why there was people arguing that it was unfair. And so then it changes how the exam was written later on to make it more fair. And then some teachers were like, well, I'm just going to give them 4 marks for this. And then, but you're not supposed to, like, it's a provincial exam, which is supposed to, everybody's supposed to mark it the same. So then, that's where controversy comes in. Makes for a good lesson today, Paul.
Yeah.
Some nice controversy. So algebraically is nice because it finds them all, right? Algebra is nice for our graphing technique because when you graph something, you find all the x-intercepts. That means you can't make more. So you can graph things very well. Now, these, like I said, these questions with volume and finding maximum volume, I think have a lot of applications in real life. Oh, I'll even tell you a story.